Physics Part 413. A typical X-ray spectrum showing the variation with wavelength of the intensity of an X-ray beam is shown in the figure. The spectrum has two distinct components. First, there is a continuous distribution of wavelength with a sharp cutoff at the shortest wavelength. Second, sharp peaks may be observed. These sharp peaks correspond to the emission of the spectrum of the target metal and are therefore characteristics of the target. The continuous distribution comes about because the electrons, when incident on the metal target, will not all have the same electron but will instead have a wide range of values since the wavelength of the emitted radiation is dependent on the deceleration. There will be a distribution of wavelengths. The cutoff wavelength corresponds to an electron that is stopped in one collision in the target so that all of its kinetic energy is given up as one X-ray photon. The kinetic energy Ek of an electron is equal to the energy gained by the electron when it is accelerated from the cathode to the anode, where E is the charge on the electron and V is the accelerating potential difference. The accelerating potential V thus determines the cutoff wavelength. The larger the potential difference, the shorter wavelength. The hotness of the X-ray beam is therefore controlled by variation of the accelerating potential differences between the cathode and anode. The continuous distribution of wavelengths implies that there will be X-ray photons of long wavelength that would not penetrate the person being investigated and so would not contribute towards X-ray images. Such long wavelength photons would add to the radiation dose received by the person without serving any useful purpose. For this reason, the X-ray beam emerging from the X-ray tube frequently passes through aluminium filters that allows these long wavelength photons. The intensity of the X-ray beam depends on the number of photons emitted per unit time and hence the number of the electrons hitting the metal target per unit time. Since the electrons are produced by thermionic emissions, then increasing the heater current in the cathode will increase the rate of production of electrons and hence increase the intensity of the X-ray beam. We've got an example for you. The accelerating potential difference between the cathode and the anode of an X-ray tube is 30 kV. Given that the Planck constant is 6.6 into 10 power raised to minus 34 joules per second, the charge on the electron is 1.6 into 10 power raised to minus 19 C, and the speed of the light is free space 3.0 into 10 power raised to 8 meter per second. Calculate the minimum wavelength of photons in the X-ray beam. Now it's your turn. A. State what is meant by the hotness of an X-ray beam. B. The Planck constant 6.6 into 10 power raised to minus 34 joules per second. The charge on the electron is blah 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 blah, and that's how we do it. The X-ray image. Well, the X-ray images are very popular nowadays in the hospitals. In the Department of Radiology, we do find them a lot. An X-ray image is shown in the figure. This is not really an image in the sense of a real image produced by a lens. Rather, the image is like a shadow as illustrated in the figure. The X-ray image. The X-ray beam is incident on the body part of the patient. The X-ray beam can penetrate soft tissues, skin, fat, muscles, etc. with little loss of intensity, and photographic film after development will show a dark area corresponding to those soft tissues.